Okay, this is remote session number 11, October 3rd. So first things, we're going to review quiz number 5. The class did really great on this assignment. So I'm glad that the material wasn't too complicated since you actually had to just watch the videos, right? My videos. We didn't have a live session. Okay, so let's see. We have the first example where we need to determine level curves. Okay. Um, Here, notice that we want to figure out what the domain is, and the domain is everything inside that circle of radius square root of 2, right? And the reason why we want to do it, because not all z values will work. Okay, it's most of you figure it out that, oh, okay, I can't put a value too big because once I square it, I get a negative number, right? So in a simplified, and I get a negative number. Okay, so that was really great. Most of the solutions included these numbers in the range between 0 and root 2, right? Root 2 is the largest value that we can pick. So what we get, these circles, okay, and they start with large radius and then it gets smaller and smaller. So that's what a contour map is. One other thing that I want to mention for contour map, we don't want to see each individual curve on a separate graph, right? We want to have an overall picture, okay? So we can kind of visualize with the height, right? Because remember those z values, 0, 1/4, 1/2, 1 for my graph, right? They represent heights. Okay, so when you come up with the graph, please put them all in one plot, okay, one XY plane, okay? And then you can use Wolfram Alpha to check, because if you just plug in plot 3D on your function, it will give you a contour map by default. You don't even have to specify it. Okay, let's see what's next. Limit. Okay, this problem was to determine if the limit exists. It does. So we evaluate this expression and we get 0 over 0, okay, which is an indeterminate form. And typically in calculus 1, if we were working with a function of one variable, we would just use L'Hopital rule, right? Well, in Calc 3, we can't really use L'Hopital rule for a function of two variables. So this is where we factor it, okay? We factor the top, okay? And then we remove that discontinuity. So that's your case of removable discontinuity. Once that's done, the function is nice and continuous. At that point, we evaluate it, we get 4, okay? So one way you can visualize it or kind of imagine what's happening here, um, the surface, right, sits in 3 space. And as we approach 4, 1, we're kind of 4 units above. So that's the z value. But at that point, there is a hole, right? There is a hole in the surface because the function is not defined at that value. The limit exists. The function is still undefined. Okay, so that's problem 2. And then problem 3 was good. So I ask you to sketch the domain of this function. We take the expression under the radical. We want it to be strictly greater than 0. We don't want it to be 0, and we don't want it to be negative, right? Okay, so 0 in the denominator, no good, and then negative for the radical. So we set it up greater than 0, solve for it. So it's everything that's outside of that circle of radius 3. So that's a problem. I believe I covered something like that in the notes, right? In the lecture. Okay, so that's your quiz. No issues with this one. You guys did great. You guys have any questions? Anything you'd like to discuss before we jump right into partial derivatives? So give me thumbs up, your favorite emoji, or some sort of indication. All right. Okay, thank you. Let's get going. Yes, monkey emoji. Thank you. Okay, so partial derivatives. Let me go ahead and switch this up. I did upload notes just this morning, but they're there if you want to use. Okay, that's what we're going to do today. No, not entire screen. I want to do this. Okay, I'm projecting my iPad. Let's see how long it will take. Here we go. Okay, so the notes are in week 7, learning materials for week 7. Okay, partial derivatives. I think this lecture on this week and maybe next week, um, a couple of things will come together. Some concepts will start clicking. So before we do this, let's go ahead and review just slightly what we've done in Calculus 1. We looked at functions of one variable, right? So let's say I have a curve that looks something like this. That looks like some sort of polynomial function, okay, f of x. And we said when we're computing the derivative of this function, right? So f prime of x, okay? What does that tell us? Well, depending on where the function is, we can think about it as the slope of the tangent line, right? So over here, our derivative would be positive, and then right at this point right here, the derivative is 0, right? So f prime is equal to 0. Here, f prime is greater than 0. And then we have change of behavior here. This is f prime less than 0. Another critical point where the derivative is 0. And then once again, the derivative is positive here, okay? So the derivative of a function of one variable tells us a couple of things. The behavior of the function, is it increasing, decreasing, or is there a point like this, right? A critical point where it changes the behavior, okay? And it also tells us the slope of the tangent line at a point. So if I were to evaluate my derivative at a particular point, right? So let's say this is point A right here. Okay, then this is slope of the tangent line. Okay, hopefully this rings a bell. Okay, all these connections about the derivative, not just straightforward computation, right? What does it actually tell us? Now, we're not dealing with function of one variable anymore. Okay, now we're dealing with a function of two variables. So f of x, y, or we can sometimes say z, is a function of x and y, right? Okay, so our functions, the graphs, what do they look like? Now they're surfaces. Okay, so x, y, z, and now let's say I have a function, some sort of surface that looks like this. Okay, just an abstract surface. Imagine it sits in 3 space. Okay, what do derivatives tell us now, right? Okay, and that's what we're going to be discussing. Okay, so here we had f prime, or we also would say df dx, right? Okay, this old notation, like old-fashioned notation, says, ooh, that's not the correct d. Let me make it just a normal d, df dx. This says take the derivative of function f with respect to x. Well, there's nothing else to take it with respect to, right? Now we have two variables, okay, x and y. Okay, so we will be able to compute partial derivatives. And first, let's talk about notation. Then we'll talk about what it means, and then we'll talk about how to compute it. So notation now will be these curly d's, df, dx. That means partial with respect to x, and df, dy. Or if you don't like that, you can also just use f subscript x and f subscript y. Okay, either one of those is fine. Okay, I kind of use them interchangeably. So whichever one you prefer, go with that. Okay, now what does that actually mean? So what we're going to do now, we're going to say, okay, if I want to compute the partial with respect to x. Partial with respect to x. What does that mean? Okay, that means we're going to hold y constant. Okay, so now imagine what that means for this picture. Okay, so if we keep y constant, and let's say we start at some point. Let's say this is a point that we want to compute the partial derivative at. Okay, so some point x null y null. Okay, I want to find the partial derivative with respect to x at that point. What does that mean? That means y is constant. So if I were to move just in x direction, just in x direction, okay, either this way or this way, okay, but y is constant, y is fixed now, so you can kind of visualize that y is just this fixed value right here, okay. The partial will tell us the rate of change in the direction of x, okay. So then df dx is the rate of change of our function in the direction of x. Okay. Similarly, what if I were to do partial with respect to y? I'm going to just go ahead and copy this and change a couple of things. You can probably guess what I'm going to change. Partial with respect to y, I'm holding x as a constant. Okay, so y, we're holding x as a constant. Okay, so that will give us what? What's the picture here? Let me put a different point here. So let's say my point is right here. Okay, so now I'm keeping x as constant and I'm only moving in the direction of y. Okay, and that derivative will tell me what is the rate of change? How is my surface changing, right? Increasing or decreasing, or maybe it's not doing either if I only move in the direction of y. Okay, so that's the intuitive notion of partial derivative. And again, I'm going to keep reminding you that some of these concepts will click immediately, right? And others not. So, and I've talked to my students in my face-to-face class, and um, they say visualization is a tough one, right? So computation is pretty straightforward, and visualization can get a little tricky, and I agree. So it might take you some time to wrap your head around this, okay? Computation is going to be straightforward. So again, let this concept just kind of sit there in your brain, and then it will click, okay? All right, so how do we actually compute it? So that's the fun part. I think that's the fun part. Okay, how do we compute it? Let's go ahead and compute partial derivatives of the given functions. So this one says first partial derivatives. Okay, which means there's probably a second partial derivative. Okay, first partial derivative, df dx of this function. Okay, let's see. Everything that has y, I'm going to pretend it's a number. Okay, so I'm going to differentiate this function with respect to x. Okay, what does that mean? So this is 2x, right? Now, y is a number. So you can kind of think about it as 3y is a number. The derivative of negative 3y times x with respect to x is just 3y. Okay. Now, 2y squared, that's a number, right? Y is constant. So first, y is constant. Okay, so that's plus 0 because we're differentiating with respect to x. Negative 4x prime, that's negative 4. 5y, that's also a constant. So we get 0 here, and then 12 is a true constant. So that's 0. So the partial derivative with respect to x of this function is 2x minus 3y. Okay. Oh, minus 4. Also forgot minus 4. Here we go. All right. So let me pause here for a second. That's your first partial derivative, presumably. What do you guys think? Does that make sense? All right. Thumbs up. Thumbs ups are rolling in. Perfect. Let's go ahead and take a look at df dy. Okay. Now, everything that has x, that's a constant, right? Y is the function. So let me maybe write this all out, right? Prime with respect to y minus 3xy prime with respect to y plus 2y squared prime, not squared, prime with respect to y. I'm going to write it all out. You don't have to do it once we are comfortable with computing these derivatives. Okay, so let's see. X squared, that's a constant, right? So that's 0. Minus, let's see, what do we get here? 3x is constant, y is a function, so that's minus 3x. 2y squared, prime of that, 4y. Next one is 4x prime with respect to y, so that's the derivative of a constant, that's 0. Here we get 5, and here we get 0. So what do we have? Negative 3x plus 4y plus 5. Now let me highlight these. Okay, what do these functions tell us? Okay, if I pick a point on a surface and I only move in the direction of x, okay, in kind of like think about along the x-axis, then that's going to give me a rate of change in that direction, and that's 2x minus 3y minus 4. And then if I pick a point on the surface and I only move in the direction of y, then it's going to give me a rate of change in that direction, the direction of y, right? So how does my surface change in? Negative 3x plus 4y plus 5, that's the function that describes that rate of change, okay? So computation-wise, does this make sense, right off the bat, like all the steps are correct, clear to you guys? Okay, then let's go ahead and work through these. Let's see if you can help me out here. dx, dy, df dx, first one. df dx. Let's go ahead and do this one. Or if you'd like to write it like this, f subscript x. Okay, so here's a more complex function, right? We have sine, and then expression inside is in terms of x and y. Okay, so this would be the derivative of sine, which is cosine x squared y minus 2x plus 4 times the derivative of the inside with respect to x, right? Prime with respect to x. Okay, so can somebody compute that for me? So what is the derivative of the expression inside the argument with respect to x? Take a moment, compute that. Okay, a couple of answers. We got 2xy minus 2. Okay, so I'm going to put it up front. So to kind of distinguish between the argument of cosine and that this expression is separate, right? So that would be 2 xy minus 2 times cosine of x squared y minus 2x plus 4. Okay, good. Okay, let's do df dy, or you can call it f subscript y. Okay, let's see. This would be cosine of x squared y minus 2x plus 4. That part is the same, right? Times the expression inside differentiated with respect to y. Okay, what would that be? Okay, I got two answers, x squared, right? Good. So x squared, that's a constant, right? So we have y, and then everything else is a constant, so that's 0. So this derivative f is x squared times cosine of x squared y minus 2x plus 4. Okay, good. All right, let's keep rolling with these. They get a little more involved, but the idea is the same. Okay, df dx, what's the derivative of tangent, right? That's the first thing. So what is the derivative of tangent? Secant squared. Okay, good. So secant squared of what's inside, okay, times this expression right here, prime with respect to x. Okay, all right. So if somebody can compute that derivative for me, please let me know. So we know secant is not going to change, right? So I'm going to put this, whatever you tell me, I'm going to put it up here. And then it's going to be secant squared of this expression. Okay, so Javier got 3x squared minus 6xy. I agree. Do you guys agree with that answer? Yeah, looks good. 6xy squared. Okay, nice. All right. Okay, 3x squared. This is all power rules, right? And then we have 6xy squared, 2y to the fourth prime with respect to x, that's 0. Good. Okay. Let's see, df dy or f subscript y. Okay, well, the second part is not going to change. This is going to be the same times. Now I would like this expression to be differentiated with respect to y. Okay. All right. You guys go ahead and tell me what we get. Okay, Carmen, you have an answer, right? So we got 8y cubed 6x squared y. We're just missing a negative, right? Okay, so there should be a negative here. Yes, okay, so negative 6x squared y. Okay, good. Plus 8y cubed. Okay, all right, that's it. Okay, what's the feel about it so far? This is just computations, right? What do you guys think? This all right? Okay, got a bunch of smiley faces. Excellent. Yeah, typically students find this very intuitive and kind of fun. Now, we're not going to go through those examples just yet, but let's think about it. Can do you think we can extend this to three variables? Right? What if I have a function of x, y, z, and I were to compute a partial with respect to x? What would I be holding constant? That's right, both y and z. Very good. Yes. So if you have a function of three variables, you differentiate it with respect to one by holding whatever is left, right? Those are going to be constant. Okay, so then in this case, you would have three first partial derivatives. Okay, now of course we can extend it to a function of 19 variables, right? We're not going to be, but in theory, it is possible. Okay, all right, one more before we look at a different flavor of these problems. Okay, so now we have a product. Okay, we have e to the power negative 2x times cosine of 3x plus y squared. So let's go ahead and compute these partials, df dx. Okay, now I've got to be careful because I have a product of two functions where x is a variable, right? So let me go ahead and write this out. So this is e to the power negative 2x prime times cosine of 3x plus y squared plus e to the power negative 2x times this portion prime, right? Okay, so the first thing that I need to do is to apply the product rule. Okay, so that's product rule. All right, now we're differentiating this with respect to x. Okay, what is e to the negative 2x prime? Okay, negative 2 e to the negative 2x times cosine of 3x plus y squared. Okay, good. Then this we can rewrite, and now we differentiate this with respect to x. So derivative of cosine is negative sine, right? And then what else is there? What is the derivative of the argument with respect to x? 3, okay? Times 3. Okay, so let me clean this up a little bit. Let's see. What can I factor? I can factor this, right? Okay, and I can actually factor negative of that. So negative e to the negative 2x. Okay, so then I get 2 cosine 3x plus y squared. And then there's also a negative here. Okay, so that gives me 3 sine 3x plus y squared. Okay, all right. You don't have to factor it if you don't want to, I just like to kind of keep it a little bit more organized. So that is your answer here. So you see, sometimes these functions get a little bit more complicated. But if you would just follow the rules, we'll get it. Okay, what about df dy? Okay, let's see. Maybe can somebody give me an answer for this? Do you guys want to give it a shot on your own? Work this one out? This one is easier. So take the time to work on it and then somebody give me an answer. Okay, let's see. Carla says it's 2y times e to the negative 2x times cosine. Yeah, okay, I got you. Okay, so times cosine of 3x plus y squared. Yep, that looks good. Okay, did you guys get this? The rest of you, if you try to do this, you can still apply the product rule here and realize that e to the negative 2x prime with respect to y is 0, right? Because it's just a constant. Or you can just keep it as a constant. And in this case, we only differentiate. Oh, this should be sine, right? Shouldn't this be sine right here? Here we go. Yep. And negative. Okay, negative sine, we have 2y e to the negative 2x. Okay. Okay, I think now we've corrected everything, right? Let's take a look at it. Is that right? Yes. Okay. Very good. So, um, again, I've said it before. My expectation is not that you get it immediately, right? You will get it eventually. Okay, and with more practice and more examples, it will kind of become a second nature to say, okay, derivative with respect to x, that means y, or whatever other variables are constant. Okay, so take the time to practice these. Now we're going to compute second partial derivatives. Okay, what are we doing here? First, let's talk about notation. So second partial derivative with respect to x, d squared f dx squared. Okay, that's the notation. Or we can do f subscript xx. Then we can have a similar notation with respect to y. So that means take the first derivative with respect to y and then differentiate that with respect to y again. Okay, or fyy. And we will also use what we call mixed second derivative. So df squared, and then here we'll say dx dy. So this one would mean what? We differentiate with respect to x first and then y. Okay, and then d squared of f dy dx, that's equivalent to fyx. Okay, taking a second derivative means differentiate twice, right? It's that same function. Okay, so let's work through these carefully. Okay, first let's compute f subscript x. What is that? Let's see. So derivative of sine is cosine. And times the derivative of the inside with respect to x. So that would be 3, right? I'm going to put it right here. Derivative of cosine is negative sine the derivative of the argument with respect to x in this case is 1. So I'm going to put it here just to show that we did do it. Okay, so let's take a look. 3 cosine of 3x minus 2y minus 1 sine of x plus 4y. Okay, let's pause here for a second before we go on. Does that look right to you guys? Because now we need to compute it again, so I want to make sure that this first step is good. Okay. All right. Now we're going to go ahead and differentiate that with respect to x again. Okay, let's see. The derivative of cosine now is negative, right? Negative sine 3x minus 2y. That doesn't change. Now the derivative of the inside is 3, so 3 times 3, that's 9. Okay. Then what happens here? The derivative of sine is cosine x plus 4y. The derivative of the inside is 1, so 1 times 1, that doesn't change the coefficient. Okay, so that's going to be our second derivative with respect to x. Okay, let's go ahead and deal with y, f with respect to y. I'm going to need more room than that, I think. Let's see. F with respect to y first. Okay, the derivative of sine is cosine 3x minus 2y. The derivative of the inside with respect to y is negative 2. Now what happens here? Derivative of cosine is negative sine, right? So I'm going to put a negative here. X plus 4y. And then the inside gives us 4. Okay, let me pause here for a moment. I know we started to go a little bit faster, right? But let's take a look at this. Does this make sense? Negative 2 cosine 3x minus 2, okay? And then minus 4 sine of x plus 4y. Okay, now let's differentiate it again with respect to y. So now what's going to happen? F, y, y. All right, this one we got to keep track of all these negatives. Let's see, the derivative of cosine is negative sine, right? And the derivative of the inside is negative 2. And then we also have that negative 2 up front. So we have 3 negatives, which means the expression still stays negative, which just becomes, oops, hello, becomes negative 4 sine 3x minus 2y, right? Y4, that's 2 times another 2 that comes from the inside derivative. Okay, the derivative of sine is positive cosine. The argument doesn't change. And now what? We have 4 and then times another 4, so this becomes 16. Okay, now if you need to write out these steps, that's okay. All right, but if you want to skip them, that's fine too. Okay, but so that's your first example of second derivative with respect to each of the variables. Now it says all four, right? So now we want to compute the mixed second derivatives, right? So let's go ahead and do f x y. How do we do that? Well, we know what the first derivative with respect to x is. We already computed, so that would be 3 cosine 3x minus 2y minus sine x plus 4y. And now we're going to differentiate this with respect to y. Okay, so we've done basically this part right here, and now we need to do this part right here. Okay, all right, let's go ahead and do that. Okay, let's see. Derivative of cosine is negative sine, and we're going to figure out what that coefficient is. Differentiating with respect to y, the derivative of the inside is negative 2. So negative, and then we have 3 times negative 2. This becomes positive 6. Okay. Then what happens here? This is still negative cosine of x plus 4y, except we have the derivative of the inside with respect to y, that's 4. Okay. All right. So let's stop here for a second. Do you guys agree? Yeah. Okay. That is done. Let's take a look at f with respect to y first, then x. Okay, we're going to take our first derivative with respect to y over here. And we're going to differentiate it with respect to x. Okay, let's see. Derivative of cosine is negative sine, right? So I'm going to keep that negative in mind. I have negative 2 and negative from the sine, so that's positive 2, times the derivative of the inside, which is 3. So 2 times 3, that's 6. Okay. Minus, let's see what happens here. Derivative of sine is cosine x plus y. Nope, x plus 4y. Ooh, looks like I have a typo here. Let's go ahead and fix that. This should be 4y. And this should be 4y. Okay, that's done. So let's see, what about the coefficient? The derivative of the inside with respect to x is 1. So this doesn't change. Okay, we've computed fxy and fyx. You guys notice anything? Notice anything interesting? They are indeed the same. These are the same. What do you guys think? Coincidence or not? Would that be true just for any function, or did I happen to just pick a function that works that way? What's your intuition telling you? Javier thinks it's all functions. It is. Yeah. So this is going to be true for all functions, and this is how you can think about it. Imagine you are standing on a surface, right? and you want to move on that surface, right? So it's not necessarily a plane, but you want to move, let's say, 4 units in X direction and then 3 units in Y direction. And then you switch it around and you say, okay, now I'm going to move 3 units in Y direction and then 4 units in X direction. The you end up at the same spot, right? Either way, okay? No matter which way you go, or the change in the function, right? Whether you're going up or down, or you're not moving at all as far as the horizontal movement goes, the change is the same. So basically, it says it doesn't matter if you're going to go X first and Y second, or the other way around from a point on a surface. You're going to end up at the same spot, which means the change in the overall function will be identical. So this is not a coincidence. This is true for all functions. Okay. So I like these kind of questions because I think they, with that, the computations now kind of make sense because like it's not just oh you're computing these symbols, right? You're pushing these symbols around. This actually means something. This is telling us that oh this is how the function is changing depending on which direction we're gonna go. Okay, so this is not a coincidence. In general, fxy is equal to fyx for all function. That is true. Now we didn't prove it, right? So this is not a proof. This is not a proof class either, so we're not going to. But yeah, I just picked a random function from your textbook and that we worked it out and it turns out that they're the same. Okay. Now if you had a function of 3 variables and you have f x, y, z, and then f x, z, y, and so forth, they all will also be the same. Okay. All right. One more thing for partial derivatives before we go into linear approximations. Let's see. Let's evaluate a function. Okay, not a function. We'll evaluate partial derivatives. So here we have a function which is arctangent function, or if it's easier for you to think about it as tangent inverse y over x. Okay, and it basically says compute df dx, okay, at negative 2, 2, right? And then also df dy at the same value. Nope, I can't fit them. So I'm trying to just use both notations so you are comfortable with seeing either one. Okay, 2, negative 2. All right, let's go ahead and compute the partials first. So partial derivative with respect to x. Okay. Do you guys remember what the derivative of tangent inverse is? Tangent inverse. Okay, so Tyler gives us the answer 1 over that sum, x squared plus 1, right? So I think about it as 1 over stuff squared plus 1, whatever this stuff is, right? Times the derivative of stuff. Okay, so 1 over y over x squared plus 1 times d dx of y over x. Okay, so now what is the derivative of y over x? Let me go ahead and work this one out. So this is y squared over x squared plus 1. The derivative of y over x with respect to x would be what? It's negative y over x squared, right? Okay, So now I'm going to multiply this through. So this would be negative y over, and now when I multiply this through, remember I'm multiplying through everything, right? This simplifies nicely. This becomes y squared plus x squared. Okay. Now if I were to evaluate this at the point 2, negative 2. Okay, 2, negative 2. What do I get? This is negative 2 over negative 2 squared plus positive 2 squared. So we get positive 2 on top. What do we get here? 4 plus 4, 2 over 8. That's 1/4. Okay, so what does this mean? Okay, that is the rate of change if I'm standing on that surface at the point 2, negative 2, and I only move in the direction of x. Okay, think about it as slope, right? It's giving you that rate of change. Okay, so that's your df dx evaluated at that point. Now let's go ahead and do the second one. Df dy. So that would be 1 over y over x squared plus 1 and times d dy of y over x. What is the derivative of this with respect to y? One over x. Very good. So this would be 1 over, okay, let me do it like this. So this is y squared over x squared plus 1. And Javier says it's 1 over x. Okay, good. Now, to make it a little bit easier to work with, I'm going to multiply everything by x, top and bottom. We can do this, right? Okay, you'll see why. It will give us a similar expression as we had for df dx. So I'm multiplying this by top and bottom by x. Now over here we have x squared. Okay, and that's going to cancel out with that fraction that's inside the fraction. So if I were to simplify this, now I'm going to get x on top. On the bottom, I get y squared plus x squared again. Okay, so then df dy evaluated at this value, what do we get? This is going to be 2 over negative 2 squared plus 2 squared. We get the same thing, right? We get 1/4. Okay. Rate of change in the direction of x, rate of change in the direction of y. Okay. All right. So we've covered a good amount so far. Let me project everything over here. Yep, that's the whole second page. Take a look at these problems. Let me know if there's anything you'd like to discuss before we move on to the next objective. All right, so partial derivatives, that's done. Okay, what is the next topic in this textbook? This is different for me because they kind of put this concept of tangent plane and linear approximations really early in the chapter. In my previous textbooks, we would cover it a little bit later. So it may be my bias talking, but it's kind of unnatural for me to make that connection. Well, I'll try to do my best to kind of un- connect these two sections. And I guess maybe one of the things they thought, oh, we covered partial derivatives. Let's go ahead and just jump into more or less applicable problems. Okay. My intuition would be to cover chain rule next. So that's what we will do in the next section. So, but I'm trying to follow the order of the textbook. Okay, so tangent planes and linear approximation. So it is going to tie out a couple of concepts. One of them is a plane, right? So we know an equation of a plane. Okay, let me remind you that we said if we have a normal vector, right? So if we have a normal vector here with, let's say, components A, B, and C. And then we had a point, right? So with coordinates x null, y null, z null, then we can come up with an equation of a plane, and it comes from the dot product, right? Being 0. Okay, so this is A times x minus x null, B times y minus y null, and then plus c times z minus z null. So all of the vectors in that plane that are orthogonal to this normal vector n, if they're orthogonal, that means the dot product is equal to 0. Okay, so that's what the equation of a plane is, the general form, and we've done a bunch of problems previously, and also you had a bunch on your exam. Okay, so planes are very important in practice because when we're working with functions that are really complicated, I'm talking like, big problems in industry, in research, things like that. We work with these functions that are so complex, that are difficult to deal with. But if we're only interested in a small portion of the domain, and it has to do with things like resources and time and things that you have limitations of, right? So we don't really necessarily need to look at the big picture. We only want to look at a small portion of the surface. Then we can approximate a surface with a plane, and we can do that with pretty high precision. Okay, so there are two forms that you see here for an equation of a tangent plane, and that's what tangent planes are used for. They're used to approximate behavior of functions that are so complicated and messy that it's not worth time and resources to deal with the actual function. It's better to just look at approximation and get results that way. And in general, once you guys, get out of college and work with real data, and you will see that we don't always necessarily get these beautiful answers, beautiful functions as our results. Most of the time, we settle for the best approximation we can get. Okay, so that's a big field of approximating, using numerical analysis and numerical methods. Okay, so this is kind of like a quick and dirty explanation of why tangent planes and linear approximations are useful. So here's your first one. Okay, your first form, implicit equation, where this is basically our equation of our plane from the previous chapter, right? Okay, except now, what is that normal vector? What is that going to be? If you look at it, what is f? Okay, f is the function. Well, it's not a function. F is the equation that describes the surface. Okay, so f is the equation of a surface. Okay, so that's our big F. And then these are all partial derivatives. That's all they are. Okay, so F with respect to X, F with respect to Y, F with respect to Z. Those are the partial derivatives of our equation of a surface. Okay, and then we have x minus a, x minus b, z minus c is equal to 0. That just follows that formula nicely. Okay, now implicit equation of a tangent plane. When do we use them? Okay, we use these, okay, when we cannot solve for x or y or z. Okay, so something like this. Let's say um, x squared plus 2y cubed plus 3z squared. Okay, we cannot solve this for one of the variables unless we do, things like plus or minus, right? Okay, so when you have an expression that's not something like z is equal to stuff in terms of x and y and things like that, then this is the equation we will need to use. Now, if you have an implicit equation, okay, implicit form, let me highlight it here. I'm sorry, explicit. This was implicit. When we have a function z is equal to a function of x and y, then we can use this equation here, and it says z is going to be computed this way, okay, where we have partials now with respect to x, with respect to y. We evaluate it at the point, and we also have a value of the function at that point. Okay, now we usually evaluate functions at the point. Okay, now these are some of the formulas you can put on your formula sheet, but I think the best thing we can do just look at a couple of examples and see that these formulas are equivalent. They're not much different. Okay, this formula right here works all the time, works always. Okay, so you can always apply the implicit one. This one works if you have a function of the other two variables. Okay, so we'll take a look at both examples, and then you will hopefully see the difference and how you can use them. Okay, let's take a look at this one right here. It says find equation of the tangent plane to the surface. Okay, so one surface, two different points. So we have two different equations. Find equations of the tangent planes to the surface, xy plus xz plus yz minus 12. Okay, so this expression right here, I'm looking at this one right here. I cannot solve it for just x or just y or just z. Okay, so let's go ahead and apply implicit formula here. Okay, so my large or my big F is xy plus xz plus yz minus 12. Okay, I'm going to go ahead and compute my partial derivatives. So f with respect to x, what would that be? That is y plus z. F with respect to y, that is x plus z. And f with respect to z, that would be x plus y. Okay, so these are my partial derivatives. Okay, I do have 2 points, so I'm going to have 2 different planes. So let's work with point P, 2, 2, 2. Okay, so that's going to be first part. Okay, what do I need to do? First, I'm going to evaluate each one of my partial derivatives at that point. So fx evaluated at P, they're all going to be the same, right? It's just 2 plus 2. Is the same as fy evaluated at P, is the same as fz evaluated at P, and it's just 2 plus 2, 4. Okay, so you can think about it as that you found that normal vector. Okay, so that's going to be your normal vector with components 4, 4, 4. Now I'm going to take that point. Let me use a different color to differentiate my answer here. So this is 4 times x minus 2 plus 4 times y minus 2 plus 4 times z minus 2. That's equal to 0, right? My normal vector, the dot product of my normal vector with all points in that plane should be 0. Oh, we can clean this up. We can reduce it by 4 and combine like terms. So on the left, we get x plus y plus z, and then -6, I'm going to move it on the other side. That's going to be +6. Okay, so here's my plane. This plane is tangent to that surface, xy plus xz plus yz minus 12, at the point 2, 2, 2, right? So it touches that surface at just that one point. And if you just look at the plane in that small neighborhood, imagine, here's your point P right here, and if you just kind of circle a small neighborhood around it, and small, it's kind of subjective, depends on what we're working with, but we can use the plane instead of the function to approximate values. Okay. Now, this function, of course, is not that complicated. We can just use the straightforward function here, right? But the point of this problem is to show what would that be used for. The idea is to use a very simple linear function to give pretty good approximations. We're going to take a look at some examples where we'll find approximations, and they're really good. So resource-wise, it's a lot more efficient to use linear functions instead of some really complicated, messy functions where computations are so busy and they get expensive time-wise and resource-wise. Okay, so that's your plane to the point P. Let's go ahead and do plane to the point Q. This one is with different coordinates. So different point, different plane, right? Okay, so first I'm going to evaluate my derivatives. Now they're going to be different. Okay, y plus z, that would be 6. And then this one is x plus z, so that's 8. What about the last derivative? That's x plus y, so that's 2. 6, 8, and 2. And now I'm going to plug that in. So this is my normal vector, right? So that's my normal vector with components 6, 8, 2. So now I'm going to use our formula for the plane. 6 times x minus 2 plus 8 times y minus 0 plus 2 times z minus 6 is equal to 0. Okay, let's see, we can reduce this one by 2. Let me move the answer over here. And once we combine like terms and everything, this is going to be 3x plus 4y plus z. And what else do we get? If we reduce this by 2, we're going to get -6 and -6, so that's -12, so +12 if we move it on the other side. Okay, let me go ahead and highlight all of my answer. So these are two tangent planes to our surfaces. Okay, and we used implicit equation. All right, let me pause here for a moment. Take a look at the solution. Let me know if you would like to discuss anything, and then we'll take a look at an example where we'll use an explicit equation. No questions, no comments? Okay, let's go ahead and take a look at this next problem here. it says find the equation of the tangent plane to the surface, and here we explicitly have z is equal to x squared e to the power x minus y, and we have a point. Okay, so let's go ahead and do that. Where is my formula? There it is. Let me go ahead and rewrite it so you can see it on the screen. This is going to be z is equal to what? That's going to be fx evaluated at AB times x minus a, right? So part of it is the same, plus f subscript y evaluated at AB times y minus b, and then also f of AB. Okay, let's go ahead and compute this. What is partial with respect to x? Now here, this is product rule, so that's going to be 2x times e to the power x minus y plus x squared times e to the power x minus y, because the derivative of x minus y with respect to x is just 1, right? Okay. Then with respect to y, what do we get here? Here we just have one function of y, right? X squared is a constant, so this becomes negative x squared e to the power x minus y. Okay, so these are my derivatives. Now I need to evaluate them. Derivative with respect to x evaluated at my point P. So I'm going to carefully plug this in. So what is this? This is 2 times 2 times e to the power 2 minus 2 plus 4, right? Well, let me write it as 2 squared times e to the power 2 minus 2. Okay, so that's 4 plus 4. So this gives us 8. Then here we get negative 2 squared times e to the power 2 minus 2. We get negative 4 here. Okay, now we're going to plug this in into our function. So z is equal to, all right, we have all of the ingredients, right? So this is 8 times x minus 2, that's my point, right? Okay, then plus, what is the slope? Negative 4 times y minus 2. And what about the value of the function at that point? That's actually given to us. That's this one right here, right? It's 4. Well, you can plug it in and check it, right? Okay, but that is just given to us explicitly. We just need to recognize that, oh yeah, z is equal to 4, x and y is equal to 2. So that's plus 4. Okay. Now, if I were to write it in standard form with, x, y, and z all on the same side, what do I get? So if I do that, so that would be 8x minus 4y minus z, and on the other side, I'm going to get 4. Okay, so that is an equation in standard form of a plane, right? That's a plane that's tangent to our surface at that point, 2, 2, 4. Okay, and here we used explicit formula. Now, I do want to make one note. Okay, so my z, this one z right here, this z, I'm going to make it in purple, is not the same z as in the actual function. And I think that's partially why uh, there might be some confusion with these problems, okay? That z now, when we write this equation right here, that z refers to a different function, right? Okay, that z is a function of the plane, right? That's the plane. Okay, the original z is the surface. Okay, so maybe sometimes it kind of helps to put subscript to kind of differentiate them. So this is z1 and that's going to be z2, right? So a different kind of z. They're not the same. Okay, they're not the same function. All right. So you could try and solve this problem using the implicit formula, and you will get exactly the same answer. Okay. So if you were to do this in implicit way, okay, using implicit form. So you need that big F, right? Your big F would be then x squared e to the power x minus y minus z. Basically put everything in one side and that equals to 0, right? So if you were to apply the steps that we did for this first problem to this function right here, well, it's not a function, right? Now it's not a function, now it's just an expression. Then you would get exactly the same answer. All right. Okay. So what do you guys think of tangent planes so far? Got any feedback for me? How does it feel? Good so far? Yeah? Okay. Then let's go ahead and use this now as come up with an approximation just to see how powerful this is, even for functions that are not too complicated. So now this next function, this next formula is not really a brand new formula because all we did say, okay, now let's call this a function L, L for linear approximation. This formula right here is exactly a copy of the one above, except now they don't call it Z, they call it L of XY. Okay, and we can apply this now to say, okay, what if we want to use a simpler function to compute values approximately? How would we go about it? Okay, so let's take a look. This problem right here says, find the linear approximation for this function. We have 12 minus 4x squared minus 8y squared. Okay. Again, in practice, you wouldn't do this because this is a simple enough function to just work with, right? But the idea is the same. We would apply this to functions that are a lot more complicated. And we have point -1, 4. Once we come up with the linear approximation, we can find approximate values for points that are relatively close to this guy here, right? And you can see that -1.05, 3.95, it's very close to that point, -1, 4. Okay, let's go ahead and solve our problem. So what do I have here? I have my function. I'm going to compute the first partial with respect to x. Now I'm working with this one right here, right? Okay, so this would be -8x. My second, no, my first derivative with respect to y now, right? That's -16y. We can evaluate these. Pretty simple. Get 8 here. And then this is -16 times 4. Get -64. Okay, so we have our slopes. So what about the function at that point, right? So f evaluated at that point. So it's not given to us explicitly. So x is equal to -1 and y is equal to 4. We can compute that, no problem. So that's 12 minus 4 times 1 squared minus 8 times 4 squared. Oops, should be -1, right? It's not going to change the answer. Okay, once we do this, we're going to get negative 120. Okay, so now we have everything we need to put it together into L as a linear approximation function. So that would be 8 times x minus minus 1, that gives us plus 1, minus 64, and then what do we get here? Y minus 4, and then plus the value of the function at the point, so that's negative 120. Okay, and then once I multiply this through, oops, this is 8x minus 64y, and what is the constant that we will get here? That's going to be plus 144. Okay, so this expression right here, this function, okay, how do we think about it? Let me put this in quotation marks. It's approximately equal to, roughly, to 12 minus 4x squared minus 8y squared, but only for points close to p, for points close to p. Small neighborhood around that point. Yeah, we can do that. Don't go too far because we're going to get a large arrow, right? So the larger you go, the bigger the arrow is going to be. Okay, but just around that point, no big deal. We can do that. So now let's go ahead and approximate it. So L evaluated at negative 1.05, 3.95. We just plug this in. So 8 times negative 1.05 minus 64 times 3.95 plus 144. And once you do this, we're going to get negative 117.2. Okay, so that's our approximated value. Now we can't compute the actual value. It's not too complicated to compute it. If we do this, we're going to get negative 117.23. That's pretty good. The approximation is so close, right? Okay. And of course, we also didn't go too far. Okay, so then you say, okay, how far can I go? Well, that it really depends on each function and point and so forth. But in general, that's a method that's used to compute all sorts of things in real life application. Okay, it's too good to be true to get nice solutions to even differential equations. Okay, or large problems where you have lots of data, lots of numbers. Most of the time, we settle for the best way to approximate it. Okay. All right, let me stop right here for a moment before we do our last portion for today, and we'll call it a day. So take a look at this solution. Let me know if anything is unclear, and then we will have one thing to do and we're done. No questions? Okay, then let's go ahead and do last thing. We're going to see how we can use linear approximation to also approximate the change in z. Okay, so change in z, how our function changes, we can approximate it by dz, which is a linear approximation. All right, so let's see how we can apply it. Let me go ahead and copy this function so you can see the equation there. Okay, so that's what we're going to be applying. All right. Okay. So compare the change in z and dz when x changes from 1 to 1.05, 2.1. So we have a small change in x and y. We want to see how that changes affects the function, right? Now, this one is straightforward. How do we compute change in z? In general, we would say, okay, so that would be f of whatever the point that you moved to, right? So let's say point B, you go from A to B, minus f of A, right? Okay, so if you start at A and you go to B, then the change in the function would be f of B minus f of A. So in our case, we start at 1, 2, we end up at 1.05, 2.1. So that would be f of 1.05, 2.1 minus f of 1, 2. Okay, now I'm looking at my function. This is my function right here, so we can evaluate this. Let's see, this is 5 times 1.05 squared plus 2.1 squared minus, and then the same, I'm going to plug in 1 and 2, right? So 5 times 1 squared plus 2 squared. Okay. And this is the actual change, and it turns out it's 0.9225. And of course, I'm using a calculator for this one. I'm not assuming we're going to do this in our head. Okay. So this is actual change in Z. Okay, so if I go from 0.12 to 0.1, 0.05, 2.1, my function increases, right? The value of the function increases by that value right there. Now, while this doesn't seem too complicated conceptually, you can imagine that this can get really messy for functions that are challenging, right? That are involved. Okay, so what can we do instead? So now I'm going to compute dz. And all it is just a linear approximation. So dz is dz dx, partial with respect to first variable, time change in x, plus dz dy times change in y. Okay, so now what do we have here? What is my partial with respect to x? It's going to be 10x. What was the change in x? Well, the change in x was 0.05, right? We went from 1 to 1.05, so that's going to be 0.05 here. Similarly, derivative of z with respect to y, that's 2y. What about change in y? We went from 2 to 2.1, so that's 0.1. Okay, let me make that note so it's clear. Okay, this is from 1 to 1.05, and this is from 2 to 2.1. So that's so we know where that comes from. Okay, so now we can evaluate it. We can evaluate this expression. Okay, for what? We start at what point? 1, 2. For x is equal to 1, y is equal to 2. So if I do that, what is my dz? So that's going to be 10 times 1 times 0.05 plus 2 times 2 times 0.1. And once I do this, my change becomes 0.90. Okay, that's the approximated. But if you look at it, it's really close to the actual. So this is approximated. Oop. Okay, right to the approximated change in z. Okay, so having these two, we can also compute the error, the absolute error. And we can kind of control it if we want to, and say, okay, if I don't want an error that's greater than 3%, that means, okay, I can't go too far from my points, right, where I'm using approximation. So what about the error? Okay, so let's go ahead and see how we compute it. We go actual minus predicted, okay, or approximated in this case. I'm using the language of statistics. So actual is 0.9225 minus approximated, and then we need to divide that by the actual, right? I'm going to take absolute value of this because sometimes we'll have minus, negative values, which is not a big deal. We want to look at the absolute error. So 100% on the outside. And once you compute this quantity, you're going to get that our error is 2.44%. It's not terrible. It's pretty good, actually. Okay. But over here, you say, okay, so what's the big deal? Why would we use it? Because this expression right here is very simple. It's simple. It's easy to compute. Now, our function that we worked with is not exactly complicated either, right? 5x squared plus y squared, that's also easy. The idea is you would apply this to really challenging functions, and that dz is still going to be just as simple, right? It's just going to be these two quantities added to each other. That's it. Okay. All right, so we are cutting really close to being all the way through the lecture. Okay, we are finished with the concepts. Okay, so I'm gonna go ahead and finish the recording. As always, I'm gonna stay online until you guys need me. But this session is done recording.